Hello class, this is a video recording of the lecture that we missed this afternoon. I apologize for having to cancel the lecture, and also thank you so much for those of you who kind of emailed me asking how I'm doing. It just, as it turned out, it's just a cold, and when I went to the urgent care, there were just a ton of people with the same symptom like mine. So you all be careful, okay? It seems like the medication is working, so I can kind of get back to business now. Um, what I will do in here is I will first make a video recording of what is missing for this node 6.0, and then I'll get started with node 6.1. Okay. So please make sure you watch both videos, and then on Tuesday I'll go over the, the most important materials in these two nodes again. Okay. So for 1D arrays, arrays are nothing but a sequential sequence of bytes, right? So if you think about this, for 1D arrays, we can have LR here, FP here. If you have an array A with 5 elements, um, keep in mind, no matter whether you have little ND machines or big ND machines, the layout of array elements always goes from the lower location to higher location. What that means is A4, the last element of this array A, will be at the high memory address, and then we'll just lay up like this. So FP is pointing over here. And then if you have another integer variable, and this is I, okay? So the offset in here is -4, -8, -12, -16, -20, -24, -28. These are the offsets of these variables, assuming they're local variables relative to FP. Okay. So this is the layout. The next thing is the name of the array, A. Right, so what is A? This is the name. If you see out this name, in fact, it is the address of the first element in the array. When I say first, is basically means A0. So the value of A, which is in fact just this thing, FP minus 24. Okay. And the reason why it's called a constant pointer is you can't change the value of this pointer. It's fixed. So this also implies if you declare an array, basically the location of this array is fixed. One important thing about arrays with respect to C and assembly is in C, for example, if I'm looking for A2, it is equivalent to say the reference A plus 2. And what this implies is we're looking for 2 elements down the line from the beginning of the array. So this 2 really represents 2 ints. So C already knows the data type, so it can do the automatic calculation for the address. But if you look at the address of A0, which is FP minus 24, the address of A2 is -16. Their difference is in fact 8 bytes. In assembly, there is no data type. We only know the size. So if you are looking at assembly, this is in C, right? In assembly, what we will have to do is we have to go from A plus, which is 2 times 4. And this will be the size of int. So in assembly, you have to do the scaling by yourself. In C, it's taken care of. So for example, in here, I want to load, this is an example, I want to load AI into R3, whatever I is. So the first thing I can do is I can first get what I is. Supposedly, if I offset is -28, so I'll first load the value of I into R3. So now R3 has a value of I. And remember, I need to do the scaling. I need to basically multiply I with 4, right? If I is 0, basically R3 will be 0. But if I is 1, R3 now should change into 4. So the way you can do it is you can do a shift to the left. 2 positions. That's in essence, you are multiplying by 4. And the next thing I need to do is I need to find out the relative location of this ith element compared with A0. So all I need to do is to add this with negative 24. This is kind of how far away down the line I'm at. And this is what the third line is. A offset is negative 24. And once you have this thing, this will be the relative offset of this ith element from A0. For example, if I is 2, you are looking at this entire thing equals to negative 16, right? Which is the exact offset of A2. And the last thing you do is FP minus this FP plus whatever this negative offset is. So that's the last load, okay? So when you access elements in an array, it's kind of easier for you to kind of calculate how far away it is from the head of the array, because normally you would know the offset of the head of the array, right? This 0th element. You calculate its relative offset, and then you just put FP, add it with FP. That's it. Yeah. Later on, we'll be looking at 2D arrays, 3D arrays, and things will basically follow the same idea as in here, except you just have more layers of arrays. That's the first thing. The second thing is the structures in C, okay, and also in assembly. C doesn't have class. It doesn't have objects. The only thing it has that is similar to class and objects is the idea of structures. So you can create a struct. A struct is basically a collection of items. You can think of struct as class, but it doesn't have any functions. It only has a bunch of member variables. That's basically what it is. If you think about this, if you have a struct called foobar with 4 integers, the way it will work is if I do something like this in my function, I say struct foobar foo, something like this. It's already in here, or it's already declared. And then you have int x. If you have these data as a local variables, you have LR here, you have FP over there. FP is pointing to the bottom. And then you have a struct. The way that the struct variables are laid out is exactly the same. It's not exactly, it's very similar to arrays. So if you look at the struct, the first variable would be the variable that you put in the struct first. So A, B, C, and D. This entire thing is foo. Okay. So it's a variable called foo. Foo doesn't contain the address of A. It is just the name of this struct, and then you have X above it. X above it. Yeah. If you look at the this is the offset, -4, -8, -12, 16, 20, 24. Okay. So this struct, the entire thing, is this struct foo. Okay. You can access the elements in this struct as foo.a will give you this integer over here. Okay. And then foo.b, foo.c, you know the idea. So let's try to fill in the offset. Foobar offset from FP, which is the beginning of this thing, so it's -20. A's offset within the struct. A is at the very beginning. B is positive 4, C is positive 8, D is positive 12. The entire size is 16 bytes. Okay. If you use standard definition.h and you can use the offset, what you see is this. So variable A's offset within the foobar struct is 0. Okay. Let's now do some translation. For example, if I say foo.d assign it to x, the first thing you got to do is you got to look at the right side of the equal sign. You got to load it. I'll just use var register R3 in here. So what I can do is I say LDR is load R3 FP D's offset is -8. Okay. And then now R3 contains foo.d. I need to put it into X, which is store R3 FP minus 24. Right, so this is the first translation. The second translation is foo.a plus foo.c assigned to X. You do similar things. So it's LDR R2. Let's say I will use R2 to store foo.a. Its offset is -20. And then foo.c, you load it again. C's offset is -12. And then add them up. Let me put the result back into R2. And then I do a store of R2 into FP minus 24. So these are the translations for that. These are the translations for this. The last exercise, I say foo.b equals to x. So the first thing you got to do is you load the value of x, LDR. Let me use R3. The choice of my registers are very random, but will be very specific in our exams or in our PAs to say what registers you should use. So the first thing I do is load x, which is -24, and then I need to do a store, and foo.b has an offset of -16, right? So these two give you that. As you can see, the member variables of a struct is just like a standalone variable, except they are all together sequentially in the memory block. Remember, the first thing you declare in a struct, it is on the top of the struct. Okay, an entire struct is laid out from top to bottom. And this is what is missing in note 6.0.